Hello everyone and welcome. In this video I'm going to talk about asymptotic notation. So asymptotic notation is a way that we have to represent the time complexity of an algorithm, meaning the amount of time that it takes to run depending on the size of the input we feed into it. Now I think this is best explained with an example, so take a look at the code that I have here. We're going to have an input size which I've denoted by n. Now the algorithm itself consists of a for loop that goes to that same n, and inside it has two for loops that also go to n, and inside of both of those for loops we have constant time operations like printing and summing. So both of these are going to be constant time operations because the time they take to perform doesn't depend on the size of the input. It's always going to be the same. So how do we represent, the time complexity of this algorithm depending on how large n is, how large the input size is? So first of all, we're going to have some kind of constant, which is going to be, the amount of time that printing takes to run, and we're going to repeat that n times. So we're going to multiply this by n. Then we're going to add some other constant, which is the amount of time that this sum takes to run, and we're also going to do that n times. And both of these operations we're going to do n times because of the outer for loop. So we end up with an equation of this type. Now simplifying this, we have c1 plus c2 times n squared. And c1 plus c2 is just going to be, some other constant because both of those are constants. So I'm going to name it c, which is a generic constant, multiplied by n squared. Now in asymptotic notation, there are a few rules that we have to simplify expressions like these. So if you have some constant times n cubed plus, some constant times n plus some constant, we're only going to keep the fastest growing term. So what does this mean exactly? Well, the first thing, we're going to cut off all of the constants, right? Because if you have a really large number and you multiply it by some constant, that multiplication is not really going to make much difference in terms of the, order of greatness of that number. So we're going to cut all of the constants. And we're also going to only leave the fastest growing term, meaning the term that has the greatest exponent. Because it's the same thinking. If you have something really large and you add something that's not as large, it's just not going to make much difference. You might as well just keep, the one with the largest exponent. So we're going to cut n as well, and this can be simplified into n cubed. Since we're talking about time complexity and asymptotic notation, we would say that this algorithm has a time complexity of O of n cubed. So if we apply all of these rules into our little expression here, we're going to end up with a time complexity of O of n squared for this algorithm. And if we were to plot this on a Cartesian graph, we're going to have here the input size on the x-axis, which I've denoted by n in this case. And we're going to have the time on the other axis. And we're going to end up with quadratic time, which is just going to be, a parabola. Time can be negative, so we're only left with the positive side of the parabola. And this is O of n squared, and it's called quadratic time. We could also have something like this. This is going to be called linear time. It is just going to be a linear function, and this is O of n. And we can also have constant time. This is just going to be, some constant. And here we're going to say that we have an O of 1. Because like I told you, one of the rules of asymptotic notation is that you drop the constants when you're simplifying expressions, right? Now you could argue that this should be an O of 0, since, we have some constant, we drop it, we're left with nothing. However, this would mean that a certain constant time operation would take 0 time to perform. And that's actually not true because every operation that we perform takes some amount of time, even if that time is constant. So for that reason, we say that we have an O of 1 for constant time. Now, in this algorithm, the only thing that's actually going to influence the time complexity is going to be n, right? It's going to be the input size. So let me show you another example where other factors come into play. So this is a linear search algorithm. In case you're not familiar with it, essentially we have an array, we have a certain element that we are looking for in that array. And with linear search, we're essentially sequentially looking at each element individually, checking if that element is, the target that we're looking for. If it is, we're going to return it. If not, we're going to go to the next element. And we're going to do this until the end of the array or until we find the element that we want, right? Now, in this case, added to the input size, we're going to have another factor that comes into play, which is the position of the element in the array, right? So in this case, we're going to have different cases. We're going to have a best case, and in this case, the element that we want is going to be the first element of the array, right? And in that case, we only have to go through one element. We only have to check it one time, and that's going to be great for us. So in this case, we're going to have constant time. We say omega of 1. So omega is going to be, the letter that we use to denote the best case. Then we're going to have an average case. So on average, the element that we want is going to be in the middle of the array, somewhere in the middle, and more or less at the position n divided by 2, right? So we're going to have to search n divided by 2 elements. However, like I told you, asymptotic notation rules, we drop the constants, so we're going to be left with a theta of n, right? Because we drop the half, and theta is the letter that we use to denote the average time complexity. And lastly, we're going to have our worst case. And the worst case is the element is going to be the last element in the array. So in this case, this means that we're going to have to go through every element of the array, and we're going to end up with an O of n, in which n is, the number of elements of the array. And for this, we use the letter O. So here we have 3 different types of asymptotic notation. We have big omega notation, big theta notation, and big O notation. Which one of these do you think is going to be the most important one to study? Well, you could argue that it is the average case, right? Because that's the most representative and probably the one that's going to happen in most cases. However, the worst case time complexity is actually the most important one because it's the one that's going to throw a threshold. It's going to draw a threshold to how slow your algorithm can be. And in most cases, that's the most important thing. So usually when you see time complexity analysis on algorithms, you're going to hear a lot about big O notation in worst cases and not so much about best and average. So again, if we draw this on the graph, we're going to have those same 2 axes. We're going to have a linear time, so this is linear search. And in case you don't know about it, there is another algorithm that's actually better than linear search, because linear search for really large arrays, it's actually going to be really slow. And we have an alternative called binary search. So binary search is going to essentially divide the array into 2 pieces each time. You don't really need to know how that works. You only need to know that it runs on logarithmic time. So this is going to be an O of log of n, which when n is really big is going to be significantly better than linear time, okay? Just so you know that this exists. And that is actually all I wanted to show you today. I hope this video was helpful. I hope you learned a lot about asymptotic notation and time complexity. Thank you so much for watching, and I'll see you in the next video.